Hello everyone, and welcome back to the series on mathematical finance. Today we're going to be continuing our discussion of our foundational principles for mathematical finance. Up to this point we've discussed simple interest, compounding interest, both discrete and continuous, and also various different types of interest rates that you definitely should know when analyzing financial products. So now what we're going to do is introduce the last of the very fundamental mathematical principles that you definitely should know for mathematical finance, and that is known as cash flows. So what exactly are they? So a cash flow is simply a sequence of transactions, such as payments, withdrawals, deposits, interest, compoundings, and so on. So for the entirety of this discussion, I'm going to be representing a cash flow as a set C, since it's technically just a sequence. So these sequence elements are going to be represented by C1, C2, C3, C4, all the way down to, for example, CM, and it could potentially go on forever as well. Now, some people will start cash flows as C0, but not necessarily. But these subscripts do correspond to units in time. All right. So if I have, for example, starting at 1 and ending at m, that would obviously be a finite sequence. And if it continues all the way down from C1 up to, say, C infinity, then that obviously would be a infinite sequence. All right, so let's actually consider a subset or a specific cash flow to analyze. So as an example, consider C to be equal to C1, C2, C3, and C4. For example, you make a payment to your friend tomorrow, the next day, and the final the next day after. And let us also view a timeline that represents the value of an account at various particular points in time. So let's assume that this is T0, T1, T2, T3, and T4. And technically speaking, this could continue onwards if we desired it to. And so our current balance, or our principal, is S0, S1, S2, S3, and S4. So I want to briefly mention why we usually don't have a C0 in a cash flow, although I did briefly mention that you could have one. If you did have a C0, which would be a cash flow that occurred at time t is equal to 0, keep in mind S0 is typically referred to as the principal balance on the account, whether it be your principal loan balance or your principal investment into, say, a savings account. So if you were to have a simple interest rate account, keep in mind simple interest rates are usually based on the principal balance, then if you were to have a cash flow at C0, for example, you could have a principal balance of, say, $500, and then let's assume after you created that simple interest rate account, you defined or made a deposit of $5,000 also at t is equal to 0. Depositing that money at that particular time is not going to give you a better simple interest rate, because the simple interest rate is just going to be based on that $500 principal, right? So that would be a case where, it's not very advantageous financially to do so. But there are going to be some financial products that we'll discuss in the future that, it might make actually more sense to define cash flows at time t is equal to 0. But we'll get there at a later time, right? So this is pretty much what we're looking at in terms of the timeline of these cash flows when they occur and these balances S0 through SM. Also keep in mind, if you want to move money through time, you can use periodic accumulation factors. For example, if you multiply S0 by alpha, that's going to give you S1. If you multiply S1 by alpha, you're going to get S2. But keep in mind, we're not just accumulating balances, we're also adding, for example, C1 there, we're adding C2 here, and then accumulating that sum into S3. And then we're adding a cash flow, for example, C3 here, and accumulating that sum into C4. So it's a little bit more different than before because we have our balance, and then, for example, we make a cash flow. For example, if it's a loan, we make a payment. If we have interest, that's going to be an increase, right? So C2 could technically be positive or negative depending on the context. So one could ask, okay, what is the value of this sequence at any point time t? So that's going to be the next thing that we're going to build. So let's, for the sake of simplicity, let's assume that S0 is equal to 0, for example. We're not going to be taking out any money, or we're not going to be making any initial balances. And let's assume that the sequence of cash flows starts at time t is equal to 1. So what are we going to have? So S1, by definition, is just going to be the accumulation of S0. And keep in mind, alpha is equal to 1 plus I, alpha our periodic accumulation factor, and I our effective interest rate. And then the balance at S1 is just going to be the future value of S0 times t is equal to 1, plus the amount of money that you deposit into the account or pay off the account at time t is equal to 1. So that's your first cash flow. But we're going to be assuming that S0 is equal to 0, and 0 times alpha is still going to be equal to 0, so S1 will just be equal to the cash flow value at time t is equal to 1. So now let's look at t is equal to 2, because hopefully this is a little bit more mathematically interesting. So again, S2 is going to be equal to the accumulation of S1, one's time step into the future, and then plus whatever cash flow transaction occurs at time t is equal to 2. But again, S1 is the same as C1, so we can write this as alpha times C1 plus C2. So that's the value of our transactions up to time t is equal to 2. So let's move one more step into the future. So we're going to have S3. That's going to be the accumulation of S2 by one time step, because we're going from 2 to 3, plus whatever transactional occurrence occurs at time t is equal to 3. But we again know what S2 is. S2 is equal to that particular object. So we're going to have alpha times alpha C1 plus C2. Don't forget your transaction C3, which could be 0, but not necessarily. And then let's distribute this alpha into this object. And that's going to give us alpha squared times C1 plus alpha C2, and then plus C3 at the very end. Let's just do one more. So we're going to have what? So S4 is going to be equal to one accumulation of S3 plus the transaction at time t is equal to 4, which is going to be equal to alpha times that particular object, so alpha squared C1 plus alpha C2 plus C3 plus that new transaction at C4. Distribute and combine powers, so alpha 3C1 plus alpha C2 squared plus alpha 1 to C3, and then we can technically write that as alpha 0 C4. So without doing any math, are you able to tell me what S5 is going to be? S5 will be equal to alpha 4C1 plus alpha 3C2 plus alpha 2C3 plus alpha 1C4 plus alpha 0C5. Now keep in mind, notice that 5 and 5 are the same exact time. Therefore, the value at time t is equal to 5 is not in the future or the past. So technically that's why we multiplied by 1. We multiply C4 by alpha to the power of 1 because it's one time step in the past. Alpha 2 is 2 time steps in the past, so we need to move C3 2 steps into the future. That's why we multiply it by alpha. If we weren't to go backwards, we would be multiplying by the discount factor nu, which is the reciprocal of alpha. And of course, we'll talk about that momentarily. But this is going to be S5, and I can actually write these powers in a slightly different way. I can write this instead as alpha to the 5 minus 1 C1 plus alpha to the 5 minus 2 C2 plus alpha to the 5 minus 3 C3 plus alpha to the 5 minus 4 C4, and then finally alpha to the 5 minus 5 C5. And why the heck would I want to do that? Because notice that those subtrahends and those subscripts are now matching. So I can write this, and this S5 actually has a more formal name. This is called the future value of these transactions, C, C1, C2, C3, C4, C5 at time t is equal to 5. Now I know you might be thinking, well, C5, what is the future value of C5 at time t is equal to 5? It is technically the present value if that is the time that you're actually interested in. But technically speaking, that's why we multiply it by 1. So let's write this in summation notation because we could have 5 million cash flows, who knows? So we can actually write this S5 as the sum from k is equal to 1 to 5 of ck alpha to the 5 minus k. Right? So that would be the more simplified way of representing that future value of cash flows. So let's actually formally define the future value. So definition. So the future value of the sequence of cash flows C, C1, C2, down to something, let's say the last value is C capital T, where T is greater than or equal to 1, at time T is equal to capital T, is given by, and technically speaking, the sequence could even go out in the future, so you can put a couple more dots there, is given by FV. So FV is going to correspond to future value. Subscript T will be equal to the sum from k is equal to 1 to capital T of our cash flow value, alpha to the power of T minus k. All right, so this is the definition, formulaic form of future value. Now let's go through a numerical example to demonstrate its use. So let's assume that we have a sequence of cash flows 50, 45, 23, and 17 that occurs at time t is equal to 1, 2, 3, and 4. And let's also assume that the effective interest rate is the same throughout each of these 4 transactions, and let's assume that that's equal to 3%. Let's find the future value of these transactions at t is equal to 4. So how are we going to do that? Well, firstly, keep in mind alpha, the periodic accumulation factor, will be equal to 1 plus I. So this is just going to be equal to 1 plus 3%, which is 0.03, which is going to be 1.03. So that's going to be our alpha. So therefore, what is the future value of these transactions? So let's draw a little picture just to make sure we know what's going on. So 0, 1, 2, 3, and 4. So we're going to be moving transaction 3 one step in the future. We're going to be moving 2 steps in the future. And we're going to be moving 1 3 steps in the future. And we don't have a transaction at 0, so we needn't worry about that. So therefore, the future value at time t is equal to 4 will be equal to what? So again, our transactions were 50, 45, 23, and 17. So 17 is in the time of interest. So we're going to be moving, again, 50, how many times into the future? 3. And then we're going to be moving 45 twice, and then 23 once, and then 17 is just going to be hanging out right there. So once you actually perform this math out with that particular 1.03 accumulation factor, you can find that this is going to be approximately equal to $206.41. So that's going to be equal to what we call the future value of those cash flows. Now, what I actually want to do to sort of give some insight as to what we're calculating with these. So let's define capital, let's do it fancy T. So T is going to be the total of our transactions. So K is going to range from 1 to 4. If you add 50, 45, 23, and 17, so 50, 45, 23, and 17, you're going to come around $135, right? So the future value equals something more than our 135. So what does that even mean? So since this effective interest rate is indeed positive, we're going to find out that the future value at any time n greater than or equal to 0 will be greater than or equal to this fancy t value. At least mathematically, we can justify that. So from the conceptual point of view, what does this mean? So this means that money has the potential, at least under effective interest rate I, to grow in value over, that's not over, but over time, right? So money has the potential under this interest rate to grow in value over time. In particular, you can grow 135 into 206 over the next 4 periods of time. So that's what this future value represents. So similar to how we can calculate the future value of a sequence of cash flows, we can also calculate something abbreviated by PV at t is equal to 0. So what do you think PV stands for? So we have future value. This is going to be the present value. All right, so it's the present value. So if you make a transaction tomorrow, the next day, and the next, what is that really worth today? So again, let's just review a couple basic things about interest rates. So let's assume that this is t is equal to 1 and t is equal to 2. And let's assume that we want to move money into the future. Then we're going to obviously be using A. That's going to be our accumulation factor, which keep in mind is just 1 plus our effective interest rate. And if we want to move money back in time, we're going to be using nu. Keep in mind that's going to be 1 over alpha, or 1 over 1 plus our effective interest rate. And this again is sometimes called our discount factor. So that's how we're going to move money back in time. So if we look at our general timeline, so if this is t is equal to 0, t is equal to 1, t is equal to 2, t is equal to 3, and we can technically go on forever. If we want to move 1 step back in time, that's going to be equal to nu. If we want to go back 2 steps, that's going to be nu squared. If we want to go 3 steps into the past, that's going to be equal to nu cubed, and so on. So if we have a cash flow at time t is equal to 1, we just need to discount that once. If we have a cash flow at time t is equal to 2, we just need to discount that twice, and so on. So therefore, the present value at time t is equal to 0, but technically speaking, you can just write PV since 0 is technically understood, is going to be equal to C1 discounted once, plus C2 discounted twice, plus C3 discounted 3 times, and so on. And of course, if we break this tradition that we can have a cash flow at time t is equal to 0, technically that would be C0 times nu to the power of 0, which is just C0. But again, we're considering the case where, we don't have a transaction at 0, else we could just change our principal balance if that was really our strategy. So writing this particular expression in summation notation form, we can just write this as what? So that's going to be equal to the sum from k is equal to 1 to 3, if we're only going up to 3, of ck times nu to the power of k. So the formulaic structure is a little bit more nicer compared to the future value. So for a general sequence of cash flows, so if we define C to be equal to C1, C2, C3, all the way up to some arbitrary number, potentially infinite, potentially finite, then what we're going to have is PV of 0 will be equal to the sum from k is equal to 1 to t. So let's actually end this at ct, and that's going to be ck times nu to the power of k. All right, so that's the general expression for the present value of a sequence of cash flows. So let's actually go back to our example of our cash flows. So C is equal to 50, 45, 23, and 17. And let's again assume that alpha is equal to 1.3. So what is this going to come out to? So what is the present value? And let's assume that this is t is equal to 1, 2, 3, and 4. So the present value at time t is equal to 0 will be equal to 50 discounted once, plus 45 discounted twice, and 23 discounted 3 times, and 17 discounted 4 times, so 4 steps into the past. And this is going to be equal to $90.18 approximately. All right, so that's the present value of those transactions. Now, obviously, the present value is less than the total of our transactions. So how can we view that? So again, we have that if I is greater than 0, then the present value of 0 will be less than or equal to the total of our transactions. So in the conceptual world, what does that mean? And you might want to pause this video to sort of see if you can give some explanation that might be relatively equivalent to the one I'm about to give. But you can say that the farther a cash flow transaction is in the future, the less it is worth today. Right, so that's one thing you could say. So, and if you want to look at a particular value, for example, if I have $50 5 years from now, is that really worth $500 today? Actually, no, it would be a lot less. Because if I were to have this 50 here, then I should be able to accumulate that into something a lot more. Because, if it's 5 years and we accumulate interest annually, then that would be alpha to the power of 5, which is obviously strictly greater than 50. Right? So this 50 is actually worth a lot less today, because what would that be today? That would just be 50 times nu to the power of 5, which obviously is less than 50, right? So that's the conceptual perspective of present value, and also in comparison to future value. So now that we've discussed the fundamentals associated with cash flows, in particular present value and future value of cash flows, I want to actually discuss a very special case for cash flows, because this is going to be very important a little bit later on. So the special case that I want to consider is if the sequence of cash flows is uniform. And what exactly do I mean by a uniform cash flow? So I mean C1, C2, C3, and so on are all equal to the same exact thing. And let's assume that that monetary value is equal to M, right? And that's obviously going to be some real number. So you actually get very special cases for a lot of these formulas, and that's actually very, very important. Because if you think about a loan, nobody exactly knows how much money you're going to pay every single month. You could pay $5 this month, $10 next month, $562 the next, and so on. So what a lot of people do is assume that you make the same payment size every month. So I agree to pay $565 every single month for 5 years. What is the present value of that sequence? What is the future value of that sequence? And that's actually going to help us be able to price certain transactions. For example, how much money do I need in order for it to be worth a certain amount today? All right, so sequence of uniform cash flows is actually very, very important when pricing things, right? But we'll get into the applications a little bit later on. So let's actually look at the present value formula for uniform cash flows, and you can look at the future value formula to sort of see if you can formulate that on your own. So the present value at time t is equal to 0 will be equal to what? Let's first start off with the finite sequence. So if we do the sum from k is equal to 1 to t of ck nu k, because that's the general formula, notice that ck will be equal to m for all k, 1, 2, 3, 4, all the way up to ct. So we can write that as the sum from k is equal to 1 to t of our monetary value of each transaction m times nu k. But keep in mind, m is just a constant and doesn't depend on k, so we can actually factor that out. So we can write this instead as our monetary transaction value m times the sum from k is equal to 1 to t of nu k. And what exactly is this mathematical object? Well, that's just an arithmetic sequence, right? And everybody should know what an arithmetic sequence is. And very important to note, it starts at k is equal to 1. K is equal to 0 is the other more common version of that. So you should know that we can write this in a more compact form, because we're not really going to do nu1 plus nu2 plus nu3 plus nu4 plus nu5 all the way down to nu to the power of 5 million by hand. Well, no, of course not. That's why we have these formulas for arithmetic sequences. So you should remember that that's just going to be equal to nu minus nu to the power of the upper bound plus 1 all over 1 minus nu. That's one of the very important properties associated to arithmetic finite sequences, right? So that is going to be how you find the present value in closed form for a uniform sequence of transactions. So let's actually close this video with a nice, peaceful calculation example, and you might want to think of how this is going to be used in application. So let's assume that M is equal to $550. Let's assume T is equal to 72. So this could be viewed as equivalent to monthly for 6 years. So think to yourself, what would you pay $550 every month for 6 years? Like, take a moment and think about what type of things could you buy with that. And let's also assume that the effective interest rate for this is going to be equal to 0.52%, possibly low, but that would mean that alpha would be equal to 1.0052. So if this is your particular structure, what would be the present value of all of those transactions? So PV0 would be equal to what? So our value is going to be equal to 550, and then we're going to be multiplying this by nu minus nu to the power 1 more than 72, that's going to be 73, all over 1 minus nu. Right? And keep in mind, what is nu? Nu is going to be equal to 1 over alpha, 1.0052. So you can use a calculator, use that, and substitute that in, and you're going to get a number, and this is going to come out to approximately, so did you think about that thing that I asked you, what could you buy with this? The present value is going to come out to approximately $32,960.95. So what type of things are priced in this particular realm? Right? But this is more of a generic example. I'm not really giving any real life context here, but you might start to see how all of these things are going to come together to build things we actually use in our everyday lives. So I hope you enjoyed this video on financial mathematics, and I hope to see you in the next one. Take care.